In this course, we will often use classes, so it's worth having another look at them more in depth. Here is a simple class that defines a rectangle. The initializer gets 3 arguments: the object itself, the width, and the height of the rectangle. And all it does in this case is that it sets ceph.w is equal to w and ceph.h is equal to h, that is, it stores the width and height, w and h, into object variables. Okay, so what happens when you create an object by saying r is equal to rectangle of 4, 5, for instance, is that first an object is created devoid of any values for its own variables, and then it is passed to the initializer that gets the first argument as this empty object created from this object method here, and the other parameters from your initializer call, and it executes whatever code you write, of course, right? So the result is that now we have a rectangle, and we can say things like r.h, and this will give us the height. Notice that in Python you can give values to variables of an object at any time. So if I want to say, I can say r dot beauty is equal to 5, whatever this means. Okay, so it's a beautiful rectangle apparently. And if I do this, then I can ask for r.beauty, right? But this is a variable defined ad hoc. If I define another rectangle, obviously that other rectangle won't have a beauty setup, right? So if you Python is quite liberal, and you can sometimes use this to your advantage, but typically you would define the object variables inside the initializer. So let us continue a moment. Here are 2 methods, area and perimeter. One is defined with this decorator property. What is the difference? Well, the difference is that I can say r.area. What happens when I do this, by the way? R is passed as self, and the rest of the parameters, which there are none, are passed as the other parameters. There are none in this case, but I still need to mention the parameters. So this will call this function, and it will return the area. So let's see whether this works. Yes. Instead, for perimeter, I can simply write perimeter. I don't need to write the parentheses. This is because I declared it via this property decorator. So essentially, the point of a property decorator is to be able to define something that when you use it, it looks like a variable, but actually it's a method, right? So it gives you a way to have computed attributes of an object that are given back to you as if you're accessing a variable. So now these are simple methods, but you can also create methods that have arguments. So let us define one, for example. I can define volume, okay, self, and height, and depth. Okay, so the rectangle is bidimensional. If I want to know the volume, it's the volume I get by filling the rectangle up to some depth. Okay, and I can say return the area, ceph.area, times the depth. Okay, so a very simple method. Now the old object that I defined is defined with respect to the old declaration, so I cannot just use it, right? I need to redefine an object. So if I have to redefine this object, of course, the perimeter method will work, but now I will also be able to write things such as r.area volume of 20, for instance, and this will give me 400. So it's important to notice the order of arguments between these and these. So this definition accepts self and d, and self comes from the left of the dot, if you will, and the d comes from the argument itself. If I wanted to define a method with 2 arguments, I don't know, d1 and d2, I don't know what those would be, but just to give you an example, this takes 3 arguments, this would be the first argument, this would be the second one, and I would need a third one as well, which could be something like this. Let me just fix this definition so that it actually runs. Okay, so I can do this, and then this would work. Okay, so essentially, compared to the use, the declaration always has one more argument, which is the object itself. Okay, so here is my definition again. This is code I'm just rerunning. Now, here I call r.volume of 20. Now, there is another way of doing this same thing. It's not common to do it, but sometimes you need it. And that is, you can use the class name dot the method name. This is just a function, right? And then you pass to it the arguments, that is the object and the parameter. So rectangle.volume of r, 20. This perfectly works. Okay, so you should think at this dot notation as a shorthand essentially for passing this argument followed by whatever argument are in the parentheses. Okay, let's talk about static methods. Consider this definition. I define a class up and down that has two methods, up and down. These methods take a string and convert it to upper or lower case. Now, when you look at this definition, there is one thing that is peculiar about it. That is, the object self is not used into it, right? I'm using here a class simply as a way to collect various functions together. This is often the case that, you know, maybe you have even some normal methods in a class, but also you have some other functions that you just like to put inside a class because that's where they belong logically. But these methods actually, or functions, don't need to touch the object in any way. They just need to compute something and return the result. So if you need to do that, the clean way to do it is not to take this argument self and not use it, but rather it is to declare a static method. This essentially frees you from the need of specifying the object, and then when you call the object, you can call it directly over the class name. So you can define a cat string, and then you can call up and down up of the string, and you get the result, right? So this gives you a way essentially to include in a class declaration functions that do not need access to the object itself. Let us continue with our look at tricks to deal with objects. So one trick that sometimes is very handy is this. If you have an object R, in our case this is a rectangle, if you say dir of R, that is directory sort of R, this gives you actually the list of all the methods that you can call on the object. So if somebody gives you an object and you don't know how it can be used, you could always do that. The list is long. It contains a lot of the built-in methods. For example, objects can always be compared. There is a way to represent them to a string. There is a way to convert them to a string. But among these methods, so usually the built-in methods start with a double underscore. Then there are also the methods we defined and attributes: area, h and w, perimeter, and volume. So this is a handy way if you get an object that you don't know where it comes from to see what's inside it, essentially. Another thing is the following. Sometimes we want to access attributes using their name not with a dot notation. You see, normally we say r.w or r.perimeter, but suppose we are given actually a string that is equal to perimeter, and we want to write here something like r.getS, except we cannot quite do this, but this would be the idea, right? We have the object R and we want to get to the S attribute of it. So the way to do it would be to say getAttr of R and then perimeter. Okay, so the result of this will be, well, in this case it will be 18. Okay, so so this gives you a way to fish out things out of an object in a programmatic way. And the symmetrical way is called setAttr. Okay, I don't know if I have an example here. Yes. I can say r.color is equal to blue, or I can say set attribute r color to green, and our color would be green, right? So let's try to run these two lines. You see, it has set r.color to be green. Okay, so this is not incredibly commonly used, but sometimes when you develop code that needs to look at objects and generic objects, figure out how they are made, and transform them, having the ability to actually list the fields of an object via dir and programmatically get and set their values can be quite handy. Suppose we want to define two classes, a duck class whose object should be able to swim and quack, and a duckling class whose object should be able to swim, quack, but also peep. Okay? So there are two ways of doing it. The official way of object-oriented languages consists in using the notion of subclass. So you would define first a duck class and define an implementation for swimming and quacking, and then you can define a duckling subclass defining also the peep method, and the implementation of swim and quack would be inherited from the superclass. Sometimes, of course, this doesn't quite work so nicely, and so you would have to define in the subclass also maybe the swim method, because maybe ducklings need to swim in a different way. They need to paddle a little bit more or whatever else they need to do, right? But still, you would maintain logically this organization that a duckling is a special type of duck. Now in Python, often you use the organization on the right-hand side. That is, you define your duck with its own swim and quack methods, and then you define a duckling just re-implementing all the methods. This is commonly done in Python in the cases in which the internal structure of the duck and the duckling are really a little bit different. So there is not so much advantage in declaring the duckling as an instance of a duck. There is not so much sometimes that you can actually inherit if you want to change the implementation altogether. And so in Python, often people don't bother and just define what logically should be a subclass in a completely independent way. Why does this happen? Well, so the point is that Python generally espouses the principle that is called duck typing. That is, if you swim like a duck and you quack like a duck, then you have a duck. Okay? So essentially Python will not often delve into questions of what the type of an object is. It will simply try to use it and try to call the various methods. If the object has the various methods implemented correctly, then everything is fine. In fact, this confers an advantage to Python compared to Java, in that it does not need to have a full hierarchy of classes in order to work, right? Its functions can be quite tolerant. A function can operate on many types of objects as long as the objects have all the required methods. A way to perhaps remember it that I find a lot of fun, but is not perhaps the official way, is the following. To me, Java is a little bit like the old British system of aristocracy and hiring, in which when the young guy comes and is to be interviewed by this, lawyer's office, the person says, Are you the heir of the Count of Worthingworth? No, sir. Are you somehow related to the Duke of Birmingham? No, I'm afraid not, sir. Well, then, next, please. Okay, so in Java, what really matters is the ancestry, right? When you declare a Java function, you say, for example, that the function f will get any parameter that is a duck. Okay, this means that you can accept an x that is a duck or an x that is a subclass of a duck. If you can quack and swim, but you're not a duck, a descendant from a duck, you are toast. That's the way of Java. And so the problem of Java, for which there are many complicated ideas to solve this fundamental problem, is that you need to have these hierarchies of classes that sometimes are there really for their own benefit, right? Sometimes you would like to say, oh, okay, but this object can also swim and quack. Can you please just use it? Maybe you have maybe you're writing a game and you have invented a way to display objects that swim and quack when you press those buttons. And yes, yours, you wrote it on the side. It's not really inheriting from a duck, but you say, please, you can animate it. When you press that, it says quack, it's just fine. Why don't you do that? And Java says, no. If it does not descend from a duck, I don't want it. I'm sorry, Maybe make duck an interface or make it a quackable interface, your business. But, I will only make quacking animations with things that have the right pedigree. Okay? In Python instead, this is much more, what the sort of American dream used to be. A guy enters in the office and the person asks, hey, can you quack? Yes, I can quack. Can you swim? I can swim, Sue. Okay, you're hired. No, it's much easier. That's the sort of way of Python. So essentially in Java and in C++, often class hierarchies and inheritance are an indispensable ingredient of the language, because if you don't have the right hierarchy, nothing works. In Python, inheritance and subclassing is basically used to save you effort most of the time. Sometimes, but this is a minority of cases, you can check the pedigree of an object, right? You can ask whether the class of an object is a subclass of a particular class. There are some applications that we will see in this class later at some point in which we will be doing these. But it's not the most common way. The most common way is more, if you will, democratic way of just trying to do whatever you want and seeing whether it works. This said, I want to show you that you can actually use subclasses in Python. We will be doing it not infrequently in this class. And so let's look at how it works. I can define a class fabric rectangle, which is a subclass of a rectangle. It's meant to be a rectangle which is not only of rectangular shape like a rectangle, but it's also made out of cloth, and so it has a certain unit cost for the cloth, okay? So the way it works is this: you define the superclass in parentheses. It's not a very sophisticated inheritance mechanism like in Java, in which you can inherit from multiple classes and etc. In Python, you can inherit from only one class. I think that's, somewhat better. It sort of limits the way in which you can tie yourself into a loop. So when you define the initializer method of the subclass, so first of all, this is optional. If you don't define it, just like any other method, the initializer would be taken from the superclass. But if you do define an initializer for the subclass, you should remember to call the initializer of the superclass init with the proper parameters. You can do it usually at the beginning. If you wanted, you could do it at the end. It's not particularly recommended. Okay, so this is an initialization for a fabric rectangle. It initializes the underlying rectangle with the width and height, and then it sets the unit cost explicitly. Okay, so this will inherit all the methods of the rectangle, and we can define additional methods, such as this cost method that uses the unit fabric cost, and if not, it uses the cost. This is a typo. In order to compute how much it would cost to use it. Okay, and so you can run this code. Okay, great. So I mentioned that in Python, even though it's not something that is very habitual, you can check the pedigree of an object. So you can check whether an object is somehow a subclass of a particular class. You can ask whether an object is an instance of a particular class. And so this fabric rectangle will be an instance of rectangle. Okay, it will of course also be an instance of a fabric rectangle. Okay, so this will also be true. Okay, so you can use isInstance to check whether an object belongs to a class hierarchy, essentially. One thing that is a lot of fun and we will be doing quite often is to create data types. That is, we want to create objects on which you can act upon using the more natural operators of a language, such as plus, minus, divides, dot, whatever else. So let's look at how we can create complex numbers. So I create a class of complex, okay, and I define the initializer to which I pass the real and the imaginary part of the complex number, okay, and I put it here, self r and the self I. Now, to give you a little bit of a preview of why I'm doing things in this way, I want to write code such as this one, which, in this moment it won't work because I haven't yet defined it. But I want to define x is equal to complex, maybe with 3 and 2, right? Maybe y is equal to a complex of 2 and 4. And then I want to be able to write things like z is equal to x plus y. So I want to be able to use the plus operator between these two objects of complex type, and I want the plus to do the proper thing. And I want to do this for plus, but also, of course, I want to do this for minus, divides, and various other operations, right? So how can I tell Python how to add two objects of my type? Python knows already how to add two integers, in which case, it's arithmetic addition. It knows how to add two lists. It is, list concatenation. How can we tell it to do these for any arbitrary object we make? So if you look at the Python data model, you can read how this can be done. And it is essentially done by defining particular functions. The add function will take as argument the object and another object, and is used to compute. So this essentially computes objects plus another object. Okay. So when you write x plus y, this calls x add of y. Okay. So when Python sees let me simplify this. When Python sees x plus y, it will reason as follows. Do I know already what plus means for these? Are these basic data types? No, they are not. Okay, so let me see if x has a method called underscore underscore add underscore underscore. And if so, I will pass y to it. Okay, and the result of calling this add method with argument y on x will be what I put into z. That is the way Python will reason. Essentially, when you try to use arithmetic operations on things that are not the basic, underlying types of Python, Python will try to look for the existence of these special methods that are used to carry out arithmetic on non-basic types. So in the case of complex numbers, what we do is this. If we add the self to other, the complex number resulting from the addition has the real part that is the sum of the two real parts, and the imaginary part that is the sum of the two imaginary parts. So I simply say self.r plus other.r as the real part of the new object. Self.i plus other.i is the imaginary part, and I pass these computed real and imaginary parts again to the complex constructor, so that I construct a new complex number that is the result of the addition. Here I do the similar thing for subtraction, of course, right? So I first compute the real and imaginary parts of the result, and then I build a new complex number that I return as the result of the subtraction. You need these constructors, right? Because what you want to return is an object of the proper type. Multiplication, yes, you simply follow the rule for complex number multiplication. Okay? And again, you build a complex number as a result. You can also have modulus square, which is the square modulus of the number, which is defined as a property. This is not an arithmetic operation. It's just something that you can use. And then, I've defined a couple of those things because I use them in defining true division. True division is the floating point division. You should read this data model documentation. It tells you all the operations you need to implement in order to implement all the various operators of the language. And this is something we do often, so we will see it in many places. You can also define equality. This is quite important. Normally Python, if you don't say anything, tells you that the two objects are equal only if they have if they are the same object. Let me show you. So suppose I define two rectangles that happen to have actually the same size. Okay, so if I define them and I ask whether they are equal, the answer is false. Okay, this is because for rectangles I didn't bother to actually define the equality operator, the equality method, and so two rectangles are considered to be equal only if they are actually the same rectangle, which is, you know, probably not what you like when you want to ask whether two rectangles are equal. You probably want the answer to be related to the you know, intrinsic properties of the rectangle, but Python knows nothing of the intrinsic properties. You really need to be explicit in defining equality, otherwise what you get is simply the same object as notion of equality. Instead, for complex numbers, we define this notion of equality that two complex numbers are equal if their real and imaginary parts are the same. And so we can say C1 is equal to complex 3, 4, C2 is equal to complex 3, 4, and then we can ask whether they are equal. And for complex numbers, we get true as answer, right? And this double equal here is decided using a call to this method. Other things work. For example, we can do C1 minus C2 plus C2, and this is equal to C1. Well, is maybe not very surprising, but this works also if we change the definition of what is C2. Okay, if C2 is complex of I don't know, 2 minus 1, okay, this equality would still be true. We can divide things, and you know, we can get things that are false. Why do we get that this is false? This is interesting. So let's look at it. So what is C1? 3 plus 4i. Okay, and what is C1 divided by C2? You see why it's useful to have a representation method times C2. Okay, you see, my equality method is a little bit too precise. You see, there is this 0, 4 at the end. So essentially here we are being too strict, and sometimes things that are very close numerically are not considered to be equal. So I think we would have to define, you know, some notion of approximation, but this is actually perhaps not so important, because this is a generic problem with comparing floating point numbers. Even when you compare floating point numbers that are real numbers, you can never really ask whether they're equal, only if their distance is smaller than a certain amount. So in fact, we could ask here, because we have many functions, so let's try to have a bit of fun. We can ask for C1 divided by C2 times C2, okay? And we can say that this is our point 1, okay? We can say that our point 2 is just C1, okay? And at this point, we can say, for example, what is, so if we do P1 minus P2, this is a complex number that's the difference of the two, right? And then we should be able to ask for the modulus, okay? Okay, so yes, okay, so we can compute the distance between two numbers. So an alternative notion of equality, for example, we could have written here, I write it, but then I will comment it out. You could say return self minus other, okay, in modulus smaller than, I don't know, 10 to the minus 3. Okay, so something like this. This would probably work. We would need to recreate the objects where we run our code. Okay, but notice that this equality now is true. One thing that is fun to do is to implement objects that can be used with the same square bracket notation as dictionaries. That is, you can say d of 3 is equal to cat, and this will assign the key 3 to the value cat, or you can say simply d3 to fish out the value and be given, the cat back. So this is done by implementing the getItem and setItem methods. Okay, you can look at the documentation here, but essentially it works as follows. When you write x of 3 is equal to cat, Python will call x.setItem with arguments key3 and cat as the value. Okay, so the setItem method is used to implement assignment to a dictionary. And when you write something like y is equal to x of 3, to fish out the value corresponding to the key 3, Python will call x.getItem of 3. Okay? So in order to create something that behaves like a dictionary to which you can assign values in this way and look up values in this way, what you need to do is implement the setItem and getItem method. Okay? And to give you a concrete example, here I wanted to implement a class that implements a time-stamped dictionary. So I want to implement something that behaves like a dictionary, but also remembers the time at which I have set the various keys to their values. Okay, so not only I want to assign a value to a key, but I also want to remember at what time I did it. It's like one of those archival systems in which you not only mark, what's the value, but you also mark when you wrote it. Okay, so to do this, I define my own object, and I will give it a setItem method to set items into this dictionary, a getItem method to read them out. And then I will be able to ask for the age of a key, that is, for how long ago did I define a value for that particular key. Okay? I also define the length, but that's kind of secondary. Okay? This is a way to define the length of an object if you want. Okay? So let's look at the implementation. So if I just wanted to define a dictionary, I could just define that inside my object there is a dictionary, and I call this self.d, just as a shorthand, and this will hold the key value correspondence. But I also put in my object another dictionary called ts for the timestamps, so that I can write the time at which each key was set. So the setItem method works as follows. So this is called with argument self, which is the object, the key, and the value, right? And in order to implement it, I first write self.d of key is equal to value. That is, I store the key value mapping inside the dictionary of the object. And then I also say self.timestamp of the key is equal to the current time. Okay? I would need to do only the first of these two lines, only this one, if all I cared for is to implement a dictionary. But I want to implement a dictionary that is time-stamped, and so I also remember the time of each assignment. The getItem method actually is just unchanged, right? Because, it's not unchanged, but it's just very simple, because I just need to look up in the dictionary D for the key K. So getItem of self k, I return my dictionary entry associated with the key k. If you ask me for the age of a key, what I do is this. I return the difference between the current time minus the time when the key was set. Okay? That's all I do. So the implementation is quite simple. Then I can create a timestamped dictionary. Look at this code. I create a timestamp dictionary and I assign a cat. Then I sleep for half a second and I assign a value to a bird. Then I sleep for 1 second and I print the cat has this value and this age. The bird has this value and this age. And you see that the cat has value 4, just as I set. And it has age 1.5 seconds and something, right? Because Python takes a bit of time to run. And the bird has value 5, because that's what I wrote into it. And the age of the assignment to bird is 1 second, so it's less, right? Because the bird was assigned half a second after the cat. Okay, and of course now I spent a little bit of time talking. So if now I ask, for example, timestamp dictionary.age of cat, I will get a much longer time, 63 seconds. Okay, and I can ask it many times, so every time it will give me a bigger value, right? I could also ask for the official timestamp. Here I just wanted to get the age of an assignment. This is not such a crazy application. It enables you to compare or sort the dictionary according to things that were defined earliest. Or newest, so it's these kind of things are useful to do. It's not such an artificial example. It is quite often the case that you take a data structure such as a list or a dictionary or a set, and you say, it almost works the way I want. If it could just remember these or do this other thing, then I would be happy. And so essentially the tools that I have given you to implement operations or to implement the interface of a dictionary are useful exactly for this. They enable you to create something that behaves like the standard objects, but actually also contain the special properties that you care about. And we will have ample occasion to do this in the class.